Hello and welcome to a new video on cryptography for everybody. Today we have a different kind of video because today we will have a look at a cipher that I created, and I created the so-called text AES. Since when I was creating videos about the AES, I asked myself if it is possible to create an AES cipher that works only on text and that can be executed by hand. And so I created the text AES. And in this video we will have a look at the text AES cipher. I structured the video into 7 different parts. In the first part I will give you a motivation why I created the text-based AES. After that we will have a brief look at the overview of the original AES and the newly created text-based AES. Then we will have a look at the 4 building blocks of the text AES, namely add round key, sub-bigrams, shift rows and mixed columns. After that we will have a look at the key expansion. And finally I will also show you a little bit of code of the text AES, and we will play a little with text AES in Visual Studio. Why did I create the text AES? In 2021 I created 2 videos about the real AES, the Advanced Encryption Standard. I created a video about the Advanced Encryption Standard itself, and then I created a video especially about the key schedule and key expansion of AES. And before you watch this video here and you don't know how AES works, you should have a look at these 2 videos. And when I created these 2 videos to refresh my understanding of the details of AES, before I created these videos, I implemented AES in C#. So when you learn how a cipher works, it always helps, at least me, it always helps to implement the cipher on my own. And while implementing AES, I thought that all of its steps, all of its building blocks could be even easily performed by hand, I thought to myself. So I wondered if I could create a hand AES or at least a text-based AES, and designed one based on my AES implementation source code in C#. And in this video here I present the result of my experiment. And one hint. The text-based AES was implemented by me just for fun. And of course it should never be used for any security purposes. First, let's have a look at my requirements. And I had 2 main requirements when I created the text-based AES. The first requirement was that it should work on a standard Latin alphabet. So instead of giving binary data to the AES, we want to give Latin characters or Latin letters to the text-based AES. And these go from A to Z, as you probably know. And then the cipher has to be executable by hand. At least the cipher, not the original key schedule, was the basic idea. Here on the right side you can see how this would work. You give plaintext or ciphertext, it's just A, B, C, D and so on, to the text AES. The key, which is with the original AES, also binary data, here of course is also text. You give a key as text to the text AES, and then as a result you get the ciphertext or the decrypted plaintext. And I have some additional, you could also say, requirements that I wanted to fulfill, and that these were that the text AES has to be based on, or at least be inspired by, the original design of AES. So I wanted to have also a cipher with 10 rounds, and it should use the same or similar building blocks. And the 4 building blocks of AES are add round key, sub-bytes, shift rows and mixed columns. Now let's have a look at the original AES and then at text-based AES in an overview. And the original AES is built like this. You enter binary plaintext, of course, 128-bit blocks of plaintext, and then you go through 9, 11 or 13 rounds based on the type of AES. So you have 128-bit, 192-bit or 256-bit AES. And based on the number of rounds then and These are based on the length of the key. You have sub-bytes, shift rows, mixed columns, and add round key. Before you go through this loop here, you also add the round key at the beginning. And then you have the last round where you only have sub-bytes, shift rows, and add round key, and no mixed columns. And for all of these rounds here, and of course at the end you get ciphertext, and for all of these rounds you have round keys. And the round keys are generated by using the key expansion here. And as I said, I created a video about the key expansion especially. And in this video I will also not go into details of the key expansion, but I also adapted the key expansion that it generates text keys for the text-based AES. And the original AES always works on a state array of 16 bytes, as you can see here in the right corner. And now let's have a look at the text-based AES. And for the text-based AES, I changed a few things. So the first thing you can see here, instead of sub-bytes, you have now sub-bigrams. What this means we will see on a later slide. I only created the text-based AES for 9 or for 10 rounds with the final round. And clearly you could adapt the text-based AES to more rounds. And then the state array, instead of having bytes here that we use to work on, we have 16 letters. And for example, we have here 16 A's, but when you encrypt using the text-based AES or decrypt, you write your text into this 16 letters state array. Now let's have a look at all of these building blocks of the text-based AES. And these building blocks are inspired or based on the original AES building blocks. And the first building block is the add round key. And as I said, of course, we always work on text data. So you have this state array here with 16 letters, and you have to add a round key. And instead of XORing these, as we did with the original AES, we just add these using plus. And then when you add the round key on the state array, you get a new state array. And each letter is just an addition of a value, you could say. So we have the A plus K here, we have the A here, the K here. You convert the letters, of course, to numbers. So an A is a 0 and the K is a 10. Then you add these, we have 10. And then you have to compute the module of 26. And this is 10. This is only the mod 26 is used that we stay in the range between 0 and 25, since we have 26 letters in total. Clearly, when we want to decrypt or decipher using the text-based AES, instead of using plus here, we use minus, which is the inverse of the plus function here. Then we have the second building block, and that is sub-bigrams. And the sub-bigrams building block consists of an S box. And with the original AES, we have the sub-bytes building block, which uses the original AES S box. But we, of course, had to replace this by something that works on text. And I created a so-called bigram substitution S box. So you can see here all letters from A to Z and A to Z. This here is our table for our S box. And when you encrypt a bigram, for instance, here you see this example KF, you look here for K and you look here for F. And then where these match, you can read out your new bigram. So we replace KF by YV. And we do this for the complete state always bigram wise. So each bigram here is replaced by using the S box. And of course, when you want to decrypt using the text AES, we have an inverse S box, which is the inverse mapping. So we have an S box where the mapping from IV is back, or it is mapped back to KF. And this is the sub-bigrams step. Then we have the shift row step, and the shift row step is a one-by-one copy of the original AES cipher. But of course, instead of working on bytes, we work on letters. So you have your state array here. We shift the first row. We don't shift the first row. We shift the second row by 1. We shift the third row by 2. And we shift the fourth row by 3. And then we get our new state. And as I said, this is a one-by-one copy of the original AES shift rows building block. Now we have the mixed columns block or building block. And in the original AES, this here is more or less complex math. And here it's very easy math because we replace the original mixed column step of the original AES by a Hill cipher. And all letters of each column of the state are combined using a Hill cipher. So we interpret this column here as a vector. We multiply this vector here then, or this vector here, with our Hill cipher matrix, and as a result we get this vector here. And then we write this vector into the new state. And we do this for all 4 column vectors. If you don't know how a Hill cipher works in detail, I also created and uploaded a video about the Hill cipher on this channel. And here's an example computation how this works. So we have this YLOR vector and our matrix here. We convert this vector into a number or a vector consisting of numbers based on the letters here. We multiply this here with matrix multiplication. We get a new vector which consists of numbers, and then we convert these numbers to letters. And this vector is then the vector that we put into our new state. And this is how mixed columns or the mixed columns building block works. Finally, we need to know how the key expansion works. As I said, I have no detailed information in this video about the key expansion. And also I created a video about key expansion of the original AES. But the key expansion for the text AES is more or less the same as with the original AES. So you generate from a key, in our case 16 letters key, we generate 11 round keys that are used in the AES rounds. And to do so, as I said, we use the original key expansion, but we changed a few things. Of course, we use the S box from the text AES. We use the same rotation, and we also use round constants as the original AES does. But our round constants are not numbers. Our round constants are these 4-letter words, you can say. We have AAAA, then we have BAAA, CAAA, DAA, and so on until we reach ZAAA, AAA. And when we need more round constants, we just start again at AAAA. And as I said, details of this key schedule are not part of this video. We input 16-letter keys from A to Z into our key schedule here. And a 16 letters key, where each key element can be a letter between A or Z, gives us a key space size of 26 to the power of 16. Why this? We have, as I said, 26 possibilities for each of these. Let's imagine this here is the key here. It's also a 4x4 matrix. We can put in here 26 different letters. We can put in here 26 different letters, and so on. So we have 26 to the power of 16 different possible keys. And so the text AES has a key space size of 2 to the power of 76.2. So I think this is quite impressive for a manual or text-based cipher. And yeah, this is quite good key space size, I think. Now that we know how the text-based AES cipher that I created works, let's have a look at the C# implementation and play a little with that. And also, if you want to play with that, you can find the source code here. I uploaded the source code to GitHub. Here we have an AES and text-based AES GitHub project. It consists my implementation of the real AES that I used to get or to understand the details of AES better before I created the video. And there's also the text-based AES inside the GitHub project that you can also use and that I present in this video. So let's check it out here. Let's check out the GitHub project and play a little with the source code. I'm here now on my desktop, and I want to play a little with the text-based AES. And to do so, first we have to clone the GitHub repository. To do so, I use the tortoise git here. You can just install tortoise git and then you can use git clone. I have the we can update this later. I have here the original or the URL that we need for AES and text-based AES. So let's just mirror it or clone it. So now we have this on the desktop. And in the project folder, you can see this AES.SLN. This is a solution file, and I just open it by double-clicking. I'm here now in Visual Studio. I put me on the right side of the screen so that you can see the source code when we open it. And as you can see here, we have in this project, we have an AES-CS file. This contains the original AES implementation, or the implementation of the original AES, not the original implementation of the developers. Of course, this is an implementation I wrote. Then you have the program CS, which contains the main method of our program. And then we have the text AES C# file. This source code file contains the implementation of the text-based AES. First, let's have a look at the program CS. And in the program CS, you can see the main method here. And it consists of, or it contains two test methods. One method that tests the AES, and then one method that tests the text AES. And I just want to test this at first, and then we have a look at the source code itself. So when you press Ctrl and F5, it compiles the source code, and then you get this as this is a console application. And you can see here we have a test for AES 128, 192, 256. And for fun, I also created an AES 512. This is not specified in the AES, but you can easily adapt it to a key size of 512-bit. For this video, interesting here is the text part. And as you can see here, here are some test encryption and decryption of text-based AES. So we have, for instance, here, hello world. This is a test of my text AES cipher. And here you can see the ciphertext. And then you can see the decrypted plaintext again. So this works with encryption and decryption. We have a first key. The first key only consists of AAAAA, so all A. And then we have a second test here. And the second test has only a slightly changed key. So instead of AAAA, we have only one B in the key. And what I wanted to test here is the diffusion and confusion, and to have a look, or at least to eyeball, if the ciphertext differ. So if this really is more or less, you could say, modern cipher, because we need huge confusion and diffusion. And as you can see here, I think not any of these letters is the same as with this ciphertext here. Could be by chance, of course, but this showed me that the cipher has more or less a good confusion and diffusion. And finally, here's a text or a test with the same text again, but with a randomly generated key. So we have here now QXF, a ciphertext, and when I restart this program, we have a different ciphertext here. This just was a test to test if it works with different or randomly generated keys. And as I said, these are the tests of AES and text AES. Now let's have a look at the program a little in detail. And we don't have a look at the test AES. Oh, we can have a look here. As you can see, for testing, I encrypted the key set all to 0. And I have our plaintext all set to 0, and I did this for each of the AES. But let's close this and let's have a look at the text-based AES. So we have here our first test. We have a text here, hello world. This is a test of my text AES cipher. As I said, the key is completely set to only to A's, and then it prints out the encrypted text. First the plaintext, then it encrypts with electronic codebook. Electronic codebook means that it encrypts always 16 letters, but the encrypted blocks are not in any way connected to each other. In fact, this is a very bad block mode of AES, but for testing purposes, I thought this was the most easiest one to implement, so I used this. And then we can see the ciphertext here, then we decrypt this, and then we get the plaintext here. And I thought it would be also interesting to have a little look at the text AES implementation. So this is the text AES implementation C# file. And when you scroll through this here, you can, for instance, find the S box here. So I created a random S box. So I didn't use any crypto techniques to create a good S box. I just randomly generated it. And I also randomly generated based on the first S box, of course, the inverse S box. And As I said, these here are numbers, and during the execution of the text-based AES, of course, at the beginning, the texts are converted to numbers, and that makes it easier to work with these. This is why the S-box here is also in this number representation. But this S-box, in fact, is the same S-box as I have shown you on the slides. These are the S-boxes. Then for the Hill cipher here, you have these two matrices here. This is the first matrix for the encryption, the Hill cipher matrix. And this is this is also the original matrix. At least the numbers here are taken from the original matrix of the AES cipher. And of course, this works. This is a standard Hill cipher then that works on 26 letters or 26 numbers. And I created for that an inverse matrix. Clearly, this here is not anymore a copy or one-by-one copy of the original inverse matrix of AES. This won't work here. Then we have a few helper functions here. We have a nice mod function, since the mod function of C# is not the mathematical mod function, so I had to implement my own mod function. Then I have two help functions here. The first help function maps numbers into text space. So you give in a number array and it returns a text array. And then we have a second help function that does the inverse. You give in a text string and it returns an integer array. So it maps from text into number space. And as I said, I always map when I work with classical ciphers from text to numbers because it's easier to work with these. Then I have a helper method, and this could also be interesting for you. This is a method that generates an S-box and its inverse and prints this out into the console. Now let's scroll down. And then we have generate random text key. This can be used to generate, as the name suggests, a random key. Now let's have a look at the primitives here. So we have add round key and subtract round key. This is for encryption and for decryption. And as I said, it takes the state. The state here is always data, and it just adds with plus the round key, or it subtracts with minus the round key, based on if we encrypt or decrypt. Then here's a debug function that can print out our S-box to the console also. Here we have the sub-bigram step. This takes our state array and uses the bigram substitution to substitute the state. By the way, this bigram cipher, or the S-box that is used in the bigram cipher, of course, is not kept secret. This is part of the specification of the text-based AES cipher. Here we have the inverse method that performs the inverse of the sub-bigram step. It uses the same bigram substitution cipher, but deciphers. Then we have the shift rows here. The shift rows is some kind of transposition cipher, you could say, and this shifts the rows as you have seen in the slides. And then we of course have the shift rows inverse function here, which does the inverse shift. Then we have the mix column step. And the mixed column step, as you can see here, uses our Hill cipher matrix to encrypt our state array using the shown Hill cipher. Then we have the mixed column inverse, which does the same, but with the Hill cipher matrix inverse. Then we have the key schedule here. I won't get into details of the key schedule, of the key expansion of the AES cipher or the text-based AES cipher. As I said, this is completely based on the AES keys expansion algorithm. What is interesting here is that the round constants, this here, are computed by using the alphabet. So our round constants are 0, 0, 0 here, but this is AAA. And we just count up here. We use A, B, C, D, and so on. Then we reach Z, and then we have A, B, C, D. So our round constants are AAAA, BAAA, CAAA, and so on. This is all for the key schedule. And finally, we have the encryption and decryption part. Here we have a helper method that helps us to prepare the plaintext. So when you want to encrypt text using the text AES, our alphabet does not contain spaces. So the spaces here are replaced by X. And also it doesn't, it does not make a difference between lowercase and uppercase letters. So we have to change our plaintext here to uppercase letters. Then we have an encrypt ECB method that goes through our complete plaintext that we put into the text AES and encrypts it. And if we have a text that is not divisible by 16, it adds X to the end because our blocks are always 16 letters, so we have to append X at the end. Same in the decrypt method. And the decrypt throws an error, since with the decrypt method we assume that we always have or always are aligned by 16. Here we have the encrypt block method that encrypts a single block using text AES, and this uses the helper methods internally to map between numbers and text. Same works with the decrypt block. And then we have the encrypt function that gets our text here as an integer array, our key as an integer array, and the number of rounds. And our number of rounds is always 10, as you can see here. And this here is the same construction as we have with the original AES. We add round key at the beginning, then we perform R rounds from 1 to R. These are then 9 rounds in our case. And we have a final round where we don't have the mixed column step. And then we return the text finally. And we have the same for the decryption, which does the same in the reversed order. I think this program is straightforward. And now let's, for fun, implement or use the text-based AES by our own. So what do you need to do when you want to implement your or use your own text AES? You first have to create a text AES object here by calling the constructor here. Then we don't need to convert between numbers. We have some comfort function for that. We can just create hello world. This is a test. And this here is then our plaintext. Then I want to print this out to the console for debugging. Then we also need a key. And you remember we need a 16 letters key. So we make 1, 2, 3, 4. And this 4 times, 2, 3, 4. Now we have our 16 letter key. And now we want to encrypt. And to encrypt, we say the ciphertext is equal to AES.encrypt ECB. Then you have to provide the plaintext and you have to provide the key. And then we can console write line our ciphertext. And of course, we also want to test if we can decrypt using the text AES. So we say decrypted plaintext equals AES decrypt ECB ciphertext, comma key. And then we can console write line decrypted plaintext. And I also want to know what we have. So we write here plaintext equals. So we will see on the console that we have plaintext equals. Then I want to see ciphertext equals here. So we have ciphertext equals. And finally, I want to see decrypted plaintext equals. Copy this here again. Decrypted plaintext. And of course, decrypted plaintext and plaintext should be the same. And we now press Ctrl F5. It should compile this, and we should see our encryption and decryption. And as you can see here, we have hello world. This is a test. This is our plaintext. Then we have our ciphertext encrypted with the text-based AES. And then we have the decrypted plaintext. And here you can see we have hello Z world Z. This is a test, and then some X's. And we have this Z here, since the text AES does not know that the space or what the space is. So it replaces internally the space by a Z. but I want to have X. So what I forgot is I can use the AES.prepare plaintext. And then we could even write this is another test, lowercase. And when we now execute this, we get here, hello world, this is a text. And this is another test, always separated with X. And then we get our ciphertext here. And then we get our decrypted plaintext, hello world, and so on. And this should be the same as a plaintext. Yeah, and this is how I implemented the text-based AES. I thought this is an interesting experiment. So is it possible to create an AES-like cipher that works on text? I think I succeeded in this. And of course, this is just for fun and for experimenting purposes. But yeah, it helps you to maybe better understand the original AES. And yeah, this is everything that I wanted to show you in this short video. I hope you liked it. If yes, please give a thumbs up. And also, you may now download, for instance, the GitHub project and play with this on your own if you're interested in. Also, if you did not yet subscribe to this channel, I also would be really happy if you do so. This really helps me to grow this channel and to make also Cryptool 2 that we use in the other videos here more popular. So thank you very much for watching and see you in the next video.